Nice. So we're recording. Yeah. Ready?
Yeah, I'm ready.
Okay. Thank you for coming today, everyone. We'll get started. Today's PhD seminar is going to be given by Matias. This is our second seminar in a row on some generalized Bayesian inference. So Matias, over to you.
Hi, everyone. So I'll be presenting my work. It's titled Robustness Scalable Bayesian Inference. It's been joint work with FX and Jeremias. Not okay. Now, a little outline. So we will start reading about Bayesian inference in general. Talk about the benefits and the problems. Then we will propose our solution, which is called diffusion score matching or DSM-based. Some of the problems from Bayesian inference. And then we'll see how DSM-based work in two different settings, change point detection and Gaussian processes. So to start, we'll talk about Bayesian inference in general, like the setting of Bayesian inference. So we have some data generated from some process P. We place a statistical model with theta, and then we try to update our belief of that parameter theta given our data. So we do it through the Bayesian posterior. So we have a posterior will be proportional to or prior time the model of given our data. So why we want to do this? Because it has a lot of benefits. One is the optimal update for our parameter belief. Then we have uncertainty quantification, and we can include some expert knowledge on that posterior. The problem is when we're doing this, to get all the benefits from that, we have to fulfill this precondition. We have to be able to correctly specify our model, meaning that there exists a theta star such that P theta star is equal to the generative process P. We should be able to also specify our prior, and then we have to be able to compute a posterior in some sense. So if we are able to do these three things, Bayesian inference is optimal and we're good to go. The problem is in real world, we usually don't have these three conditions fulfilled. We usually have a misspecified model, even for example, because we have outliers or we are not able to fully understand our process or generative process P. It is really difficult to specify some priors or meaningful priors in general. So people usually, that's this. Usually use uninformative priors or meaningful priors. And then sometimes since we need to compute an integral to compute the posterior, then it's really hard to compute the posterior. So if we are in this setting, the update rule is not optimal anymore, and the uncertainty quantification is not correct. So is it clear? Any question? Cool. So in my work, I focus on these two problems in misspecified models with hard computation. So I'll try to propose a way to deal with misspecified models without increasing the computational cost of the Bayesian posterior. Misspecified model is really big, so I'll focus primarily on outliers misspecification. An outlier is an extreme observation where we assume it comes from a different genetic process. So we have like we observe a contaminated version of the genetic process B. And here we see how Bayesian inference works in the presence of outliers in two different settings. Here, some regression problems where we have a bunch of outliers and we try to predict the true genetic process, and it failed with our model here, our Bayesian model. We will enter into these two problems later, but I can show you why this is important and how Bayesian inference failed these two settings when we encounter some outliers or model misspecification. Yeah, it's clear. So why is Bayesian inference not robust to outliers? One way to see this is because Bayesian inference relies on the KL divergence, which is a not robust divergence, meaning that if we have some outliers, the KL will move above. And how Bayesian inference relies on that? Because we can rewrite the Bayesian posterior as we have before, but now rather than consider our model here, we will consider the exponential of minus some loss function here. And if we plug in the log minus log function, minus log likelihood, we will record the standard posterior. So the minus log likelihood can be written as the KL plus a constant that doesn't depend on the model. So yeah, if we write this way over here, we obtain the standard base posterior, which is not robust because it relies on the KL divergence. So the question is, can we choose a different divergence or a different loss to obtain robustness at the same time without increasing the computational cost of computing the posterior? This method of replacing the loss there, it's called a generalized Bayes method, and that therefore we call it a generalized Bayes posterior. So yeah, this is the main idea. Try to replace that loss by different loss that give us robustness and computability. Yeah. Okay. So the loss that we propose, or the divergence that we will propose to use, is the so-called diffusion score matching, which is basically a weighted version of the score matching. But people don't know what score matching is. It's basically the expected square distance between the score function of the model, in this case, these two measures, B theta and B, where B theta is our model and B is the generative process. The score function that the score matching use is the gradient of the log density. So yeah, the standard case where the W's are just identity, the real case is the score matching that everyone knows and propose algorithm. But generalize this later and apply and put this extra weight over there, which will be crucial to get robustness in the posterior later. What is the problem of that thing is we need to be able to access to the density of the true generative process, so we cannot apply that directly to our posterior because we don't have access to the density of that of the true generative process. But we can rewrite that this discrepancy using some iteration by part to obtain that form, which is way easier to handle because the true generative process only appears to an interpretation here, and we don't and then we have a constant that doesn't depend on the data and the model PD. So we can approximate that expectation with classical mean, right? Using the empirical measure of theta, right? And then this will be our loss function that we will try to apply. We will use in our generalized Bayes posterior. Is it clear? Yeah. So yeah, DSM-based will be just that. This will be our solution. Just apply or use our DSM or DSM divergence, as another loss function, and that will call it DSM-based. But this is our proposal. So the question is DSM robust or scalable in some sense, or we will get the property that we want to solve these Bayesian problems. First, we discovered that we have a conjugacy prior for a conjugacy property for DSM-based. What does this mean? It means if we have a model from exponential family, which is this is a big family of models. So every like popular model that we use are from exponential family, for example, Gaussian, beta, gamma, and so on. Then if we choose a prior square exponential, then your posterior will be square exponential again. You have this conjugacy property with exponential families and square exponential priors. Why square exponential and not Gaussian? Because sometimes your theta only take positive values, so you can use like a truncate Gaussian or something like that. So it doesn't have to be a Gaussian, it can be like a square exponential form. So you also know the normalization constant, then you will have your posterior in closed form. This is just the forms of mu and sigma in the posterior. And what is really nice about DSM-based as well is that you can compute your sigma at time t using your sigma at time t-1. So you can use DSM-based as a kind of online updating belief. You can use it in an online way. So we have this conjugacy property. So we are able to compute the posterior in closed form when we are using exponential family members. But what about robustness? That's the one that we care most. And here we can see an example with some contaminated model, contaminated data here. It's a Gaussian with a contamination at time t, at time 10, for example, sorry. And then you have two different posterior, the standard posterior and or DSM posterior. And you can see how our posterior concentrate more in the correct data, whereas the standard base predicted like get influenced by the contamination at time. So this picture tells that we should be robust, in some sense, or we would like to quantify or show the robustness of our method. So we will use some standard robust statistic to prove robustness of the posterior. This is for an estimator, not a posterior. But if you have an estimator theta hat, and you have a contaminated distribution of that form, so the standard contaminated distribution, you compute the influence function of that estimator, means how much a contamination can move your estimation. And that's called an influence function. And if the influence function is bounded, meaning that an contamination cannot change your estimation that much, then your estimation will be robust. So an example here, we have the mean, right? The influence function of the mean is just the contamination, which if you put the superior is infinite, so it means the mean is not rules, right? Clear? Because this is like this thing. Cool. So this is just for estimator, but we want to estimate, estimators, but we want to apply to a robust or posterior. We can see and we can define the same idea for posterior. So we will call a posterior influence function. The influence of the contamination in the posterior, right? And again, we'll call a posterior robust if the supremum of that influence function is bounded. But now the influence function depends on y in the contamination and theta to your parameter, right? Because we can see our posterior as an estimator at each theta. So in the influence function, we have two parameters, and it has to be uniformly robust over the posterior. We will try to use that definition, but the problem here is like working with the posterior itself. It's kind of difficult because you have to deal with the prior and all that kind of stuff. So thanks to Takuo, simplify this property, and we only need to care about the loss. And he proved that for a posterior of that form, which is the form that our posterior has, we only need to study the divergence over there. So we defined this in the same way as before, the sensitivity of the divergence at theta and perturbation y, as the same idea as before. And if the sensitivity fulfills these two conditions, then our posterior will be robust. Yeah, just that. So what about our DSM posterior or DSM base? Basically, we proved that if we consider a model from the exponential family, and your prior is square exponential, and then your weight has this form, follows this form, then your posterior will be robust by your model specification. So yeah. So basically, in the setting where your model is from exponential family and your prior is a square exponential, you get conjugacy and also robustness to model specification. So yeah. So we show that the DSM-based that we propose has closed for update for exponential families, and also is probably robust via smart choice of W. Any question about that? Yeah.
So here, the choice of W ensures that the supremum over influence functions is finite.
Yeah.
Is there a way of updating it so that you can choose your W so that the supremum is some chosen critical value, or is that not that interpretable?
Oh, yeah, definitely. We didn't go went there. We tried to prove like some properties or like conditional overview. Then we weren't able to do it, but yeah, definitely you should be able to do it.
The mapping sort of process,
Yeah.
you could put a.
Yeah.
Does your choice of W have some sort of like intuitive meaning when you pick?
Yeah. It tried to decrease when the line at the tail of the line. Like you just try to get the maximum. Like try to those two see those two. Yeah, try to decrease where at the tails. Just don't care about the tails. So yeah, observation of the tails.
Is this, I'm sort of using this as your definition of robustness, is this used for a certain sort of equivalent thing? When you have sort of constrained observations? So, I mean, so I think of like I mean, from my survival problem, you know, you won't have a value over it's like
Yeah.
so you won't have a value over certain.
Yeah.
But then if you're on a stress set, you still have outliers.
Yeah.
But you kind of, your actual can only take certain values, but you stay within that stress set.
Yeah,
So, I don't know.
Yeah, it could. Yeah, I mean, I think you could turn your W, for example, to get that property, but like some truncation on your like boundaries on your parameter. Yeah, I think.
When you find, sort of boundary on the observation.
Yeah, on the observation. Yeah. Because this is basically what like you like the observation rather than metrics over to zero. So if that way is equal to zero, then the zero will update for the observation.
Maybe also to add this, like this is a very coarse definition of robustness. There are more refined versions. For this, it's quite difficult to say anything because you have these two arguments you need to do. There are refined versions of this in the literature. Well, you're looking at breaking down parts, for example, or you're looking at rather than what's the maximum damage you could do. You're looking at the rate of change as to the way should be. So you look at
Slightly different.
yeah, definitely. So you can look at the Wikipedia article, that's fine. But there's lots of different versions that you can value different things.
So yeah, that was a proposal, and we will see how this works in two different settings. First, change point detection. So change point detection is basically trying to find shifts that we want to model differently. For example, here we would like to model that way, and this is like a clear change point. Then we will model that in a different way. Or in this case, for example, where we have like a bounce back. So this we really want to react in that event. So that's more like an outlier and not a change point, right? So basically a change point will be a important enough shift, so we want to model that a different way. What's the Bayesian way to do this? It's called Bayesian online change point detection. It's basically model the time between the present observation and the last change point, and call it the run length of the segment. So here, for example, we have a process with two different change points, right? So the run length will replace by 1. Then contrast change go to 0. And replace change point 0 again. For this to work, we need a probability model for the data, or parameter prior, as usual, Bayesian inference, and then we need some prior on a run length. So we infer the location of the change point via the run length of 0, and then we compute the 0 of the run length in the data. With some algebra, this nice one where this zero just iteration this fashion. Here we focus on medium parameter are C-1. So here the basic consider the data after your change point. For example, if you're in this one, you just consider these 2 points with the zero and the makes sense because you assume that your data, you model your data in different ways. The standard procedure appears to the predictive procedure, right? So we have this Bayesian online change point detection. Again, the BOCD, since it's a Bayesian method, will not be robust. And the solution is use or DSM BOCD, which is basically replace the standard procedure with the DSM procedure, and we will get robustness to model misspecification or outliers. As I said, it's just the method will just replace the standard procedure with our DSM procedure. And yeah, we obtain better performance, improve the fall detection rate. This is a well-known benchmark for change point detection, where the Bayesian procedure are number false change point for the most important. Yeah. And finally, this is a nice property that we have here. We didn't discuss much, is that we even get closed form updates where in cases where the standard procedure doesn't have closed form. We know for standard procedure that every member of the family when you say prior, right? Well, we don't know the convert prior. We know it just up to a normalization constant, meaning that you won't have the posterior closed form. You will get it without the normalization constant. So yeah, since our posterior will always be Gaussian, you always know it in completely closed form. So for example, here we model the process as a gamma distribution. This is just an example of the UK bond yield, and we find some change point there which match with some events in the UK. It's pretty nice.
Sorry.
Yeah.
The gap in here is a bond.
No, the model is over the observations. You will for the running you use put like a prior, and usually you use like a hazard function to assume you have at some point you will have like a after any like an end point of iteration, you assume they be a change point or not, just like a prior knowledge. Is it clear?
Yeah.
Cool. Well, this is change point detection. So as we can see, we have better performance in terms of false rate detection, and also we have some advantage over computation over the standard POC. So finally, what time is it? I'm too fast. Okay. Finally, we apply this method to Gaussian processes. This is slightly different because now we don't have a parameter there. We will try to extend this idea of DSM procedure to non-parametric procedures. So a little recap about Gaussian processes. F follows a Gaussian process with mean n and current k. For every subset x, the vector of evaluation of x will be a normal distribution or multivariate Gaussian with mean m and covariance k, where k is just the matrix of the matrix. Yeah. People use Gaussian processes to solve regression problems, where the setting is the following. We assume we have an unknown function f, and we have some data x and y, where the data come from a noisy observation of the function f. And to do Bayesian regression, you compute the posterior of f will be proportional to your prior f. So you want usually one is on y, right? And your prior sort it's like the standard non-parametric regression setting in Bayesian inference. Is it clear, right? Cool. So for regression setting, you assume a Gaussian prior, a GP prior. In practice, people usually use a Gaussian likelihood, mainly because you will get closed form. This is one of the main properties that people want to keep about Gaussian processes, have these closed form outputs. So yeah, so this is Gaussian process. You assume you have a Gaussian prior, a Gaussian observation, and then you will get a Gaussian posterior. And if you see here an example, if you have some synthetic data, you want to do updates. Work pretty well. So your posterior will be also Gaussian, and you will be able to compute it in closed form. The problem again, if you put some layers or synthetic layer there, the GP will go all over the place. People usually fix that by changing the likelihood. You could change the likelihood. You can put like a more heavy tail observation model to taking into account the outliers or something like that. But the problem is like if you change your likelihood, then you won't get closed form observation posterior. Then you will have to do some approximation to a posterior, and then it will be really, really slow. So the main issue with all the small method above is that they are very, very, very slow. So the solution again will be use a robust posterior that will keep closed form updates, but being robust to model specification. So the same idea as before, we change the posterior. The posterior piece zero, where the loss function would be the efficient formatting. And here we have to change it because now it's overview only on the mix will depend on X and Y. So now it has two inputs, but that's the main difference from the parametric model. So yeah, if you use our loss function as originalized posterior, then you will get closed form update again. Here, for posterior with pulses, we will be again recaptured with a big similar code with some Gaussian posterior. Let's see the other changes here. Where before we have density here, and now we have these diagonal modulus of the weights. So you cannot see that here, but for RCGP or the total RCGP, which is proposed and GP, the GP with all zero will match for the GP without taking failing. Yeah, no layers. Any question? Yeah.
Talk a little bit about the calculating weights and dimensionality for that.
Yeah, that depends on the choice of W. So later with the or it shouldn't be that was used like square or that verse it shouldn't be that. That's what.
So it's no.
No. So that's the main thing. We have the same complexity as the standard Gaussian process of being books. Yep. Just this like saying this is a question that we have to study later. We are planning to study the convergence before, but since I will very well. Oh yeah. Sorry. Yeah, my bad. Oh yeah, perfect. So yeah, if we follow again, since we are in a non-parametric setting, we cannot apply the same definition of robustness that we have from before. So we will try to define a posterior inference function in this setting and show robustness for this setting. We will use the fact that our posterior are Gaussian, so we have everything kind of in closed form. So how we will define the inference function? Well, we will measure the impact of a single outlier on the posterior by computing a distance between the posterior with some data and a posterior with one contamination in the data. So you take any point in your data and you contaminate it with like as much as you want. and Z, right? So if you compute this distance, and the idea is like for every contamination, the posterior shouldn't move that much, because if a contamination or outlier can change your posterior a lot, then your posterior won't be robust, right? So we show, well, it's really easy to prove that the standard Gaussian processes are not robust. This goes to infinity really, really fast in a quadratic, quadratic equation. And we show that if you select the weight that form, it's going to be plus, or your posterior function will be bound. Yeah. So here, directly modifying. Because if you provide some model, we actually have explicit function in YFC, and even YFC see how quickly the right size becomes that. So even if you're operating this kind of calculation, the loss is 7 that's really expressing, you can just do it what we do. It's just techniques. Yeah, sorry. Yeah, definitely. Since that's so you have these two different functions closed forms. You can study them all. We just showed that that's bounded, but yeah, it's very important. Depth. In our paper, we track some states during quantitative weight with some condition over the weight that make the posterior plus. So you can play with the weights. This is I put that weight because this is the weight that we use in the experiment, but you can play with the weights. So yeah, we compare against two different methods. One is a Gaussian process with a student variable. And the other with a Gaussian process. So you have like a model for a layer and a model for outliers. We put some outliers. It's and some standard machine learning benchmarks, and we show that we met from small bus at their results, but also in competitions. So that's the main idea. We have robustness, but at the same time, we have closed forms, so we don't increase the computational cost of the method. But yeah, in summary, standard base is great, but it's not robust, and it has some problem when you fail fulfilling this assumption. So existing methods usually are robust or scalable in some sense, not both. So we can kind of rectify this by proposing this DSM-based posterior, which are probably robust and have this conjugate property, and we show the DSM applied in two different settings. Yeah. Any question? Any questions? Yeah.
Could you talk a little bit about the about false negatives? I think there was one change for the one something looked like a change.
Yeah. That one.
Is there some reason why your method would affect false negatives?
Yeah, that's true. Maybe it's too conservative again, because you will have some delays in this sense to find a change point, because if you're robust, you need to have more time until you assume there's or like infer there's a change point in that point. But if in that period of like weights, the model doesn't change that much, then it should be assumed there won't be a change point, something like that. That's my estimate.
All the standard is so triggered.
Yeah.
But it's just the other force.
Yeah. That's my guess.
Do you get somewhat certainty quantification
For that
as well? Like,
yeah. I mean here.
so would it capture?
Yeah, this is actually a posterior, so it's the problem with is the EOCD in general is concentrate really fast in the posterior. So yeah, after like 2 or 3 or 10 observations, you control a lot. But this is actually
Okay. So. Yeah. Any other questions?
Yeah. Like outliers, more specification. Yeah. Yeah. It's a good question. I mean, these kind of results here, this result can be extended not for like the definition of part, but it's not for a different observation. So as long as you more or less specify in the sense like you have some more and a contamination, then this makes our method should be fine. More difficult that kind of specification, I don't know to.
I have a similar question. The bond yield example.
Yeah.
If the bond yield goes negative.
Yeah.
But you so if it's positive.
Yeah, no,
Like,
yeah, I won't.
it's still robust in this.
No, you shouldn't. Because you're trying to model your model is still, it's still a beta distribution, so you won't be able to go to, I mean, what do you, yeah, yeah,
But then your posterior influence, I guess, would still be found. So you take. So it's still count. So if you're probably.
yeah.
That's not.
Right, that's because you still belong to the. Which is also.
Just has 0 marks.
Yeah. Yeah.
Maybe response to what you asked, it is a key question. Realize the definition. Say, what? Plus. Well, it's not. To look at. This time it means that. We focus so much on issue stuff. So, that basically origin of the bus. Reasonable. No. So that's what the reason you look at it is one of this, for example, bigger Gaussian, not really how. In the tables, but you have 2 dips in it. Let's say I was taking the book. Yes, selected. So anytime you have small line, and that is fully low. So like if not.
Yeah.
Detection.
First
of all, I don't think 3 methods that we're comparing.
The standard Bayesian online checkpoint.
Are there any pre-practice counterparts of change one
Yeah.
compared to base?
No, mainly because no, we didn't compare about that. Why? Because frequentist method usually assumes some form of the model. For example, you usually assume the Gaussianity in your model. So, for example, for for the bone yield, you won't be able to do it because have like we will put like a gamma distribution there. Well, yeah, no, we didn't compare with pharmacies.
Practically, what's in use in practical or change.
Mhm. BOCD is standard is the standard there. It's one of the standard there.
Any other questions? I don't think we've got anything online. Any other questions? I might drop one quick one.
Yeah, sure.
So this is all kind of where you're assuming somewhere you're still working in intellectual property.
Yeah.
I guess. Have you looked at any examples sort of outside of that where you, so I guess in that case you lose confidence
So you will just go USC.
and whether this still provides you with sort of some help with computation, whether there's anything this kind of affects the geometry of your posterior in some way to support that.
Yeah, this is a good question, and I think we should think about it. The thing is like in these two settings that because the DSM base appears trying to solve the problem in the patient in the change point detection, and here you want conjugacy because here you're computing this time t. So if you don't have conjugacy, then that's things really slow and it doesn't work at all. And then we stand to Gaussian processes where again conjugacy is really important. But yeah, this is a thing that we should study.
We have looked at this stuff, like, I mean, you have reticle spec.
Yeah.
So.
Yeah, you can.
There's a wide range of applications for this outside of functions. And it's actually, I don't think it's expendable, that like the thing that makes these school matching is the school matching.
Because it doesn't, it's normalization. Yeah. You don't need a normalization constant to compute the score matching because you're using the score here, where the score, since is the grade on the log density, then the normalization constant go away. So you can use it for unnormalized models.
Okay. So it's for example,
yeah.
When you offer these normalizing the sums of the terms and you get rid of them. And then you're basically making a doubling in time of the singularly track. So you can just understand X and see something as opposed to having to approximate the normalization within your X's, which is quite important. So there are definitely applications for this outside of the.
Yeah.
Yeah. And so if you do this, so again outside the copy, you still get like issues with your posterior? Like, is there some sort of universal thing you can say about the posterior using this, or is it?
No. Yeah. It's a problem specific, I think. Yeah.
Matias, thank you for the nice talk. Can you hear
so I
me?
think we can thank Matias again. And our next talk is about this time next week. So hopefully you see us. Thank you, everyone.
Matias, can you hear me?
Can you hear me now?
Or Dominic, sorry,
That's okay.
Hello.
if you want to ask your question, maybe unmute yourself and yeah, we can.
Yeah.
No, just thank you, Matias. It was a very nice talk. Shall I ask you now? I just have a very simple question.
Yeah.
So as far as you understand, the thing you suggest performs better than the simple GPs in all terms. So is there any clear disadvantage over simple GPs, or do the people is so promising that people will do research on this new thing rather than the previous one?
Yeah, if you don't have outliers, GP may perform better. We didn't see like the other method perform really worse without outliers.
Okay.
But yeah, as
Okay.
your weights are not that, I think the main disadvantage is that the weight that we propose depend on the prior mean. And if the
Okay.
prior mean is really misspecified, then our method won't work that well. So yeah, relies a lot on the on that.
Okay, thank you very much. Thank you very much. So I also interrupted you way back.
Okay.
Thank you. It was very nice talk.
Thank you.
Thank you, everyone online.